Swayam Prabha. Digital India. Educated India.
Welcome back. So far we have been doing extensional semantics. This is the last session in our series, and in this we will deal with intentional semantics. First of all, we need to understand what intention is in this sense. It is not desire or something. It is something different. We shall see what it is and how it is different from extensional semantics. And then we will see practically two models of intentional semantics, and then we will see intentional logic a bit, not much. This is not a very detailed session because intentional semantics is very intense, and it should take a very long time. This is just to give you a taste of intentional semantics and intentional logic. So, what is the difference between intention and extension? So, the value or the denotation of the word dog is the set of dogs, and cats is the set of cats. These are extensions, but when we talk about meaning, this is not the only thing we talk about. Suppose somebody who knows English sees Laika, the dog that was sent to space and it never returned. Now, when such a person who knows English sees Laika, they say that this is a dog. Look at this categorization. Now, what makes them categorize Laika under a dog? So, it is not that that person has seen the extension of the meaning of the word dog, or rather the extension that is associated with the word dog, but still that person has something in mind that makes them sort of conclude that this should be categorized under a dog. So, that thing is the intentional meaning of the word dog. Remember, we have dealt with sets and functions and nothing else, but now we will look at some other element, some other meaning element, namely the intention. The extensional meaning of a word may change. In fact, it has to change. This dog denotes different sets at different times, because some dogs die, some are born and stuff like that. So, it is time variant, model variant. We will see the meaning of model variant set, whatever model variant meaning. Intentional meaning does not change that way. It is the understanding associated with a word. Though it is that element which told me, look, this is a dog. So, it is not the set of that is identical to the value of the denotation of the word. Intentional language, we need to look at intentional languages. This I quote from our textbook, that is Doughty Wall-Peters, and they say that a definition, it is based on the intentional language is based on a definition of denotation for all expressions, not just for a single state of affairs, but for many possible states of affairs. We need to understand what this means. Now, the first intentional model we will see is the tense semantics. And also we need to understand why this is intentional. So, we start with a with kind of a paradox given by W.V.O. Quine in his Word and Object. George married Mary. Mary is a widow, hence George married a widow. Now, definitely this is not a good argument. What is the problem with an argument like this? When George married Mary, she was not a widow. So, after George died, Mary became a widow. So, George married Mary. That is perfectly all right. This sentence is correct. Mary is a widow after George has left us. Hence, George married a widow. Is it true? No. But so far, we haven't seen any weapon, any tool to detect the problem in an argument like this. We shall see such a tool. Let us consider this sentence: John is asleep. It is not true for all times, because John does not sleep all the time. It rather applies to some moments of time. We introduce the set I and the linear ordering this. These are two elements now we require. What is I? I is the set of time points or moments. Let us deal with 3 time points. We could have more, but let's start with 3 time moments: T1, T2 and T3. And I, this thing can be interpreted as I is earlier than J, or I is before J. So, or J comes after I, or something like that. Then this order looks like this. This says that first T1, then T2, T2, T3 and T1, T3. Now, definitely this actually tells us some other thing. This talks about transitivity. If they told us, the textbook told us this is this relation is transitive, they need not give this at all, because it would be part of it. What is transitivity? A relation is transitive when a relation R is transitive when R x y, and if and only if R x y and R y z holds, then R x z holds, right? This is actually transitivity. I don't need this if. So, yes, if this holds, if this holds, then that holds. For example, taller than is a transitive relation. So, if you have Tom, Dick and Harry, if Dick is taller than Tom and if Harry is taller than Dick, then Harry is taller than Tom, right? So, by doing this, they are trying to achieve the effect of transitivity without introducing transitivity, without imposing transitivity on this relation, this ordering relation. Okay. So, we now need a model, a temporal model. This is a revised version of L1. Now, previously, if we remember, we had just 2 things in our model: one A, the set of individuals, and one F, the value assignment function, and also we had G, but remember G was not really part of the language or part of the reality. G is an in-between thing, but still G was part of everything. Here we need 2 additional things: I, as already we have introduced I, and also this ordering relation. Now, the description of M, at least we are not changing the extension of names all the time. I think this is also very significant, but anyway, we are not getting into it, not changing the extension of names. Now at T1, so now f has to assign values to non-logical constants. It doesn't assign value to, it doesn't assign a value to just a constant. Now it assigns a value to a pair. So the pair includes the time point, right? So for example, it will take T1 and D and then will assign the pair a value. So depending on T1, D is B. So across all the time points, we can see that D1 remains B, D remains B, and across the time points J remains A. So we can see this, but M, the denotation of M changes. So this is the extension of M at different times. So in the first moment, that is T1, all three A, B, C are M. But in the second moment, so it is like asleep. Say in the first moment all A, B, C are asleep. In the second moment only A and B are, and in the third moment only C are. So it's something like that. So we can see that now. Previously f would take just one alpha, one singular element. Now it is taking a pair. That is very important. It takes the pair, the pair, the time you call it name, whatever, the time name pair, and then it will give that value. Okay, so then we need to compute something after having reached this. Let us compute this thing, that is all x mx implies mj with respect to m, T1 and G. For this we need to go back, we remember this and we need to go back to the model. All x mx implies mj. Okay, all x mx implies mj with respect to T1, I think. Yes, T1. I'm ignoring the rest of the index, so just T1 will do. This says that what is the value of this with respect to T1. Now let us look at this. Is it true that for all values of x at T1, mj is the case? So let's check whether it comes true. At T1, this is the value. So there are three things. So that is, three elements are A, B, C, but just two names are given. That doesn't matter. So the point is whatever applies to, so all three will be there. For example, M, J, M, D. Suppose C, the name of C is I think the name of C is actually originally it was N. It doesn't matter. Let us make it N. So then let us check whether this is true. If MD, then MJ. Is it true? So yes, J is A. So if at this moment, if D means B, if B, then A. Yeah, that's true. And then the second, so M, what is the value of MJ? J is A, so it will be M, that is the value of M takes J is A. So it will be 1. So as long as this is 1, we don't have to calculate anything more, because as long as this is 1, this thing cannot be 0 at any moment, simply because when the consequent is 1, it has to be 1. So it could be 0 only when this is 1, the consequent 1, and the antecedent is 0. Otherwise, if the consequent comes to be 1, it has to be all the time 1. So we can see that the value of this will be 1. Now, like every other systems, we'll see the rules of tense semantics. So basically there are two rules and then two different versions. One is the syntactic rule, and corresponding to that is a semantic version, like most of the other things. We now introduce two new operators. One is this F, the very special F, and very special P. Now this F stands for future and this P stands for past. So if phi is a formula, then f phi is a formula, and if phi is a formula, then p phi is also a formula. And the semantics of it, the first one, if phi is a formula, then the value of f phi with respect to mig is 1 if and only if there is some I prime in I such that I is before I prime, and then with respect to that I prime phi is 1, otherwise it is 0. What does it mean? In plain words, it means that when I say that John will smoke, I say that, for example, I say that at the time t2. So what does it? So my basic sentence is always John smokes. This is in the present tense, like the present time. Now this means that, so this is the basic, that John smokes should be true at some time Tn, provided n is after 2, right? This means the ordering relation. That is, in some future time, John smokes is true. If that is the case, if in some future time John smokes is true, then now John will smoke is true. Similarly, the meaning of if phi is a formula, then the value of p phi with respect to mig will be 1 if and only if there is some I prime in I such that I prime is before I, and this is the case, that is with respect to that I prime phi is 1, otherwise p phi is 0. So when I say that John smoked, I say that, say at T2 once again, it means that once again John smokes is true with respect to, say, sometime m, such that m is before T2, right? So this is how we understand these things, these rules. So the basic is always the present tense. Then the present time, if the present time is I, the future time is I prime, is an I prime such that I is before I prime, and the past time is, say, I double prime such that I is after that. So this is how the meanings of the values of these expressions are to be calculated. Now we are going to compute this thing. All x, for all x, fmx implies pmx with respect to time t2. So just remember fmx, pmx. We just get back to the model without which we cannot compute. Just write down for all x f mx implies pmx with respect to t2. So look at t2. So what does it mean? For all x, if m applied to a future time, there is only one future time, that is with respect to t2, that is t3. So, if m applied to a future time, that is t3, now here it is so it applies to c only, then it applies also at a past time, then n applies to that also at a past time for all x. Now, there is only one case to be checked, because in the future time m applies to just one thing, that is c. We see that in the past time too m applies to, that is m is predicated of c, that is m is true of c. Therefore, this will be 1. Remember, this is 1 with respect to t2, that is this time, this is 1. Now, we are doing proper tense semantics. We are trying to give sense to most of the things. Now, this is somehow equivalent to the future continuous tense. Not exactly, but somehow, like you can understand it rather talks about something that will never end. So, it is an endless thing. So, it says that g phi is identical by definition. By definition, g phi is neg f neg phi, that in future neg phi is not possible. In future, there is no future time in which it is neg phi. That means it does not talk about the beginning of phi, but it says that phi will continue happening in the future times. So, that operator is g, and then h x is something like the past perfect continuous. It says that h x is by definition neg p neg x, that in the past neg phi has never happened. It has, phi has always been the case, right. So, it is something like something like this, as long as you can go back phi was the case. So, this is h, this is g, as long as you can go forward phi will be the case. So, two different, so this is a picture of g, this is a picture of g, and this is a picture of h. So, this is how, now you can also see that we can do several things by using this this model. We can decide different we can decide natures of different relations. We can do several things actually. If you look at the textbook, you find a lot of exercise, lot of solved problems, lot of unsolved problems, but we cannot do anything more because we need to do two more things. The second extensional model is modal semantics. Why do we have modal logic or modal semantics in the first place? Modal semantics was needed in order to distinguish between truths of two types. So, for example, look at the fact that the Ganges is in India. Had it not been in India, there would be no logical problem. Logically, it could be. So, I can think of a picture in which the Ganges is not there in India, but it is in some other country. Say it is in Vietnam. So, that is why I can say that it is possible that the Ganges might not be in India, or it is possible that the Ganges might be in some other country. So, this is a possibility. It is possible that the Ganges might not be in India. It is an actuality, and then we also talk about necessity. What is it? It is necessarily true that the sum of the three angles of a triangle, we are talking about Euclidean triangles, the sum of the three angles of a triangle is equal to 180 degree. this is necessary, because we cannot think of a world in which this is not the case. Whichever world we think of, this must be the case. We need to talk about little, not very much, we need to talk a little about these possible worlds. We should remember that the model we are dealing with here is a very basic model. It is not a very sophisticated model of modal semantics, because that is not required. This is just to understand, it is the starting point, then we could improve on our knowledge of modal semantics, but this is just introductory. Now, but even then we need to understand possible worlds. So, what is meant by a possible world? Is it a world consisting of different things? Is it a parallel universe? No, it is not. A possible world is exactly this world, possibly with one difference. For example, when I say that today I am doing this lecture in Kanpur, I can say that I might be doing this lecture at Varanasi. Now, am I talking about a different world? No, I am talking about this very world with all these elements, the world that consists of me, this lecture, so many other things, but with one difference. The difference is in that I am doing the lecture in Varanasi, not in Kanpur. So, a possible world is not a different world, but it is kind of a conceptual arrangement, not arrangement, I do not know, I am not finding proper words to describe it, because we need to do it in a very informal manner, and I also am trying to be very informal. So, a possible world is a world accessible to me. I can think of it not like I can think of this world, but it is not a parallel world or anything. It is this very world, slightly different, possibly slightly different. Now, this is one very important thing. So, when we talk about logical truths, so there are all different possible worlds, say W1, W2, W3, and say W2 is our actual world, that is WA, the real world where we are, and the world of actualities. And now, something like a logical truth, we call it, say, T, capital T. So, a logical truth will be true here, will be true here, will be true here also, but a contingent truth, that is something like my doing a lecture in Kanpur, or Delhi's being the capital of India, those are true here. So, we call such a truth C. It is one here. It does not mean that it will be one here. It may be the case that it is 0 here. It can also be 0 here, not that it has to be 0 here, but the point is, a necessary truth is a truth which has to happen with respect to all possible worlds, but a contingent truth, a non-logical truth, is true only with respect to at least one possible world, not in all possible worlds, right? That is the difference. So, this is how we differentiate between logico-mathematical truths and ordinary truths, say even scientific truths or anything else. So, now we go to the rules. Like most of the other systems, we have just two rules here. One, the syntactic rule, that is, if phi is a formula, then necessary phi is a formula, and if phi is a formula, then possible phi is a formula. What does that mean? So, here is the meaning. If phi is a formula, then the value of necessary phi with respect to m, w and g is 1, if and only if for all w prime in w, phi, the value of phi with respect to m, w prime and g is 1. As I was saying, that because it is necessary that the sum of, we call it the triangle truth, that is the sum of the 3 angles of a triangle is equal to 180 degree. This is necessarily true. Why? Because it is true with respect to W1, it is true with respect to W2, and also with respect to W3. And on the other hand, a possible truth is true only with respect to at least one W prime, not in all. So the point is, in at least one it has to be true, otherwise it is not even possible. What about something that is not true, that cannot be true of any world? It's a contradiction. For example, something is at the same time, so for example, take this, P and not P. This cannot be true of any world. So this is a logical contradiction, right? So what is true, what is necessary? A logical truth, a tautology. For example, P or not P. Something is either P or not P. So that is, and any other thing, most of the other things would be in between. They are contingent truths. So for example, the very fact that the Ganges is in India. Okay, so we now go to the different other rules. So now, for example, we can see that if phi is true in all possible worlds, then phi has to be true at least, right? So this is one thing. And if phi is true with respect to our world, then at least it is possible that phi is true. We need to consider these two rules, and these are definitional. So when I say that phi is necessary, I am saying that it is not possible that not phi. For example, when I say that it is necessary that the 3 angles of a triangle, or it is necessary that something is either P or not P, I am saying that it is not possible that it is not the case that P or not P, right? So and so these are definitional. We very easily understand these rules, and then a few others. We are going to compute, for example, this thing. I just need to add one thing which is intuitive. When we say something, say for example, when we just say phi, if there is no other index, we say that with respect to W. W normally means this actual world. So those details actually are not there in the textbook, but we need to understand. So without any possibility or necessity, when I just talk about something, it is with respect to this actual world. So if we remember that in tense logic, in tense semantics, the basic thing was the present tense. Here also the basic thing is the actual world. So if there is no other index, then it is normally the actual world. So but then we can all the time add an index. In that case, by default it will take the actual world, but when I mention the world, it will be, the calculation will happen in terms of that very world. So now we are going to compute this thing. So possible MD with respect to W2, we need to get back to the old world, to our model. W2 is this, possible MD, I think. What is the value of it? W2. That is this we have to consider. the value of D is B. So it is saying that it is possible with respect to W2, which means that in at least one world, MD is true. Is it the case? We can see that yes, of course, because about it D means B, although with respect to W2 it is not true, but in at least one accessible world, that is this one, that is W1, it is true. So this will come to be true. Now we will see that here W2 is not doing much in this formula, but in this one W1, the index, will do a lot of things. If we remember this, all x mx implies necessary mx with respect to W1. So we get back to it. With respect to W1. Now we have to do quite a bit of computation. Now you see, with respect to W1, this will be with respect to W1, and this will be all worlds, right? So this is saying that for all x, if m applies to x, that is if m is true of x, then it is necessary that mx, then in all possible world m is true of that x. Now we need to check the value of m in W1. It is just two things, a and b. So there would be two cases, ma and how do I determine these two things? Because of W1. Without W1 I couldn't have done that. Now are these true? If MA, then it is necessary that MA, that is in all possible worlds MA, which is not true. MA is true, but this is not true, because in W2 that is not the case. So therefore we can say that this will be actually 0, because this gives 0 for at least one value, that is for A. We can see that not that m is true of A in all possible worlds, right? It is true of A in two worlds, but in the second world it is not true, right? So if we just add A here, it would be actually true, but because we couldn't do that, it is not true. So the value of this will be 0. So then so this is how we can see that we can do a lot of calculations here, and this is the final bit, intentional logic. Already we are doing intentional semantics. Intentional logic has a very special agenda. What is it? I have quoted this diagram from this textbook, Logic in Linguistics, which will help us see the whole thing. This is kind of a summary of whatever we have been doing. So we talked about the Frege philosophy of language in our previous sessions. We did that for quite some time. Now this is a formal understanding of the Frege principles. So what does this diagram say? It precisely says that you take any linguistic expression. What happens is, we have a function called the general interpretative function that takes the expression, and that itself is a function. So this general interpreting function is a function which takes the expression and yields the sense of the expression. We remember the difference between sense and reference, right. Sense is the intention. So, we are now actually entering the field of intentional logic proper. So, so the general interpreting function takes the linguistic expression and yields the sense or the intention of the expression, and then the intention itself is a function. So, here is a function which takes an expression and yields a function. That function takes the possible worlds, and so the argument is the possible worlds, the world time pairs, and then it yields the appropriate extension in different possible worlds depending on what it takes. Now, I give one example of that. This was my teacher who taught me formal semantics. His name is Professor Gautam Sengupta. This was his favorite example, the President of India. Now, we will see a lot of President of India here. Now, G, or the general interpreting function, takes this phrase, the President of India, and then now this will be the intention part of it. It is the sense of the expression, it is not the real expression. It takes the expression the President of India and yields the sense of it, and the sense takes a pair. It considers all pairs, and then depending on which pair it takes, it will yield meanings. For example, when it takes the actual world and 2019, it yields the extension of it, that is the President of India at 2019 in WA, who is Ramnath Kovind. Now, had it been WA and I do not know, had it been 2009, then it would have given some other extension, Pranav Mukherjee. So, depending on, I hope I am correct, depending on the pair, the extension will be yielded. This is the idea. So, there are two functions involved here, the general interpreting function and the sense. Sense itself is a function. The general interpreting function works in the following way. Once again, I am trying to be very lucid, so sometimes non-technical, therefore, sometimes not very tightly correct, but so the tightness is not there, but I do not want to have tightness here as far as this understanding is concerned. We just need to see what is happening. So, for example, suppose I do not know English. If I do not know English, my general interpreting function cannot even take the President of India as an argument. It can't. It can take this phrase only when I know English, right. So, it is something like not that all switches are put on in our understanding, in our brain. Some switches are put on, some switches are turned on. So, when I hear something which is favorable, which I can take, what I first get is the sense of it, the intention of it. Then, depending on the world time pair, I get the extension of it. So, this is how I understand something. So, this is a path from an expression to its extension. So, the intention of the extension of the expression is pretty much in between. So, this model is very, very important. Then we will talk about a paradox Frege talked about. We definitely did all these things before. Now, we are going to do the same thing in a formal way, that is we are now going to do a symbolic representation of that, and we want to compute now things. So, what is the problem? I try to once again remember the problem. The problem is when two things are the same, you can interchange them salve veritate, preserving the truth value. For example, it is true that the President of India, which is abbreviated as P, is the chief of Indian Army. This is also something I learned from Professor Gautam Sengupta. I didn't know this before. This was his favorite example. The President of India is the chief of Indian Army, and right now that person is Ramnath Kovind. So we are abbreviating. So the chief of Indian Army is a constant C. Ramnath Kovind is K. Now consider the sentence, the President of India is a man. We are not changing the tense or the world. We are sticking to the present tense and to the actual world. So it can be abbreviated or it can be represented by MP. So M means man. So salve veritate, without changing the truth value, preserving the truth value, then we can say, because of MP we can say MC, because P and C are the same thing, and so we can say that MK. Now what is the point? The point is the truth value of MC depends on the truth values, the value, the denotation of MC depends on the denotations of M and the denotation of M and the denotation of C. The denotation of M takes the denotation of C as an argument. This is what Frege was trying to say, that what contributes towards the denotation of the whole sentence is actually the denotation of each part, right? This is what he said. And so one test of this theory was this thing, that if two things are co-referential, then they are interchangeable. So because it is the same denotation, right? So it doesn't matter which word we are using here. What matters is what comes here. So because the denotation of C is the denotation of P, I can use this interchangeably because they are the same thing. But we also have seen that there is kind of an apparent failure of this case, where it is here. Suppose John knows Ramnath Kovind, and John knows that Ramnath Kovind is a man, but John does not know that Ramnath Kovind is the President of India. Suppose he thinks that still Pratibha Patil is the President of India. So let us take this sentence. John believes that the President of India is not a man. So which could be, this is a bad formalization, but we start with this. John believes that the President of India is not a man, and John believes that Ramnath Kovind is a man. Look, there is no incompatibility as far as these two sentences. They're perfectly compatible, although neg MP and MK are not compatible provided P is K. But although P is K, they are compatible. This is paradoxical. At least this is apparently paradoxical. To solve this problem, Frege suggested that things like belief and think, belief, all these things are referentially opaque. That is, if something falls under the scope of believe or think, then something very different happens. That is, we are trying to suppose we are trying to compute the truth value of Bell J MK. So the point is, it should be the function of Bell, and that should take first the denotation, not the function, the denotation of Bell. That should take, because this is the object, that should take the denotation of MK, and that should take the denotation of J, right? And then we should have some value 1 or 0, but that is not the case. That means it seems that this is a case of a violation of the Frege principle, that the truth value of a sentence depends on, or the denotation of a sentence depends on the denotations or the references of its parts, because here we see the failure, because maybe what John believes is not true. So, for example, this bell J neg MP, here neg MP is not true, but even then, if John believes that the President of India is not a man, then this sentence is perfectly true. It doesn't, the truth value of it has no connection with MP or neg MP. How is it that here the reference of MP or neg MP is not even affecting the truth value of it? Ideally it should. Ideally it should affect the truth value of the whole sentence. To solve this problem, we need this intentional semantics. Now, what does it mean? According to Frege, when a formula or a sentence occurs within the scope of something like think, believe, it does not give its customary reference, which is its truth value, but it gives its sense as the truth value, its intention as the truth value. That is, when I say that John believes that the President of India is not a man, I am not saying that John believes in a truth value. I am rather saying John believes in a thought. The thought, we may remember that the thought of a sentence is its sense. Now, according to Frege, in this case, we have to rewrite the whole thing. We will do the rewriting later, but the point is, according to Frege, when you have a construction like bell J neg MP, actually what you do is here the denotation of bell takes first not the reference of MP, but the sense of MP. John believes in a sense, and then the denotation of John is the subject, right? Now, this should be the ideal thing. Here, it's not the denotation or it's not the reference of the sentence neg MP, because the reference is a truth value 1 or 0. In this case, it is 0. It is not bell 0 and then J. This is not the case. Rather, it is this structure. This happens only when a sentence comes under the scope of something, it is referential opacity. So, it comes under an opaque context like believe or think. Now, how to express it in terms of our logical notation? We have to make rules for doing it. So, this is a syntactic rule. If phi is a formula, any formula, then this thing phi, we call it, I don't know what we call it, cap phi is a formula. Semantics, if phi is a formula, then the denotation of phi, it should be the denotation of cap phi is the intention of phi. So, if phi is a formula without any cap or anything, its denotation is its denotation like this. But when it occurs, when phi occurs in an intentional context within an opaque context, it is not phi, it is actually this cap phi. And how do I know this cap phi? I know that from the predicates. The predicates in this case is always think or believe or something like that, right? Now, what happens is we now have to rewrite this. As I said, this was wrong. This bel j MP as bel j neg MP as bel j cap neg MP. Now, there is no contradiction between neg MP and MK, provided that P is K. There would be a contradiction had there been no cap, but the moment you have a cap, all contradictions are gone and you perfectly understand what is being talked about. So, so that is the difference between just phi and cap phi. So, we can now write, for example, we want to write that. So, when we want to, so the point is, the moment we want to talk about the referential opacity, the opaque context, we have to bring the cap. Although the cap is not seen explicitly, it is all the time there in an opaque context. And if it is not there, then you could accuse Frege for saying whatever he said, but because of the existence of this cap, you cannot do that. So, so this is more or less the intentional logic of Frege, and we'll conclude the whole series. I just want to not summarize, but just want to say what finally we did. We concentrated mostly on extensional semantics, and we considered different models of that, starting from propositional semantics. Then we did predicate semantics, that was our focus, and then we did, that was first order predicate semantics. Then we did second order, higher order predicate semantics, which was basically L type and L lambda, and then finally we just got rid of the extensional model and we did this intentional semantics, and that is pretty much what we wanted to do. So, thank you very much.